Now I explain the concept of degree variance. Before that, I need to define a mathematical operator or the averaging operator over the sphere, which we need to use it for driving the equivariance. This operator is defined as M operator, M E brackets equals to 1 over 4 pi delta G integral over sphere E bracket the signal and the surface integration. E is the statistical expectation operator. Now I write this equation or this operator a little bit simpler because I need to apply it often in my derivation. Let me define this simply as M operator. When I say M, it means the average over the sphere based on the mean value theorem, which will average the signal, and a statistical expectation will take the average of the stochastic part of the signal. What does that mean? The true gravity field is not smooth, but the normal gravity is. We have already defined what is the normal gravity field. The normal gravity field is actually an average or mean gravity field. So the distance or discrepancies between the true gravity field and the normal gravity field, which I show it is here with red, this and this, they are actually anomalous quantities, which we already discussed all of them. Gravity anomaly, gravity disturbance, geoid height, deflections of vertical, derivatives of disturbing potential, and so on. So as you see here, I have the true gravity field and I have a normal gravity field, and I subtract them from each other to get the anomalous quantities. It is exactly similar to things that we have a data and I take the average and remove the average from the data. And what remains is called actually residual. Actually, residuals are anomalous quantities. Also, why is it important? Let me compare it with a set of data, x from x1 up to xn, and measurements. And I take the average, x bar, and I can compute the variance for this data set. The residuals, which I show it by epsilon here, should have normal distribution with average x bar and the variance s squared. It is very similar to the true gravity anomaly, to gravity field. The true gravity field is reduced for the normal gravity field, and the x bar is equivalent to the normal gravity field. Then we have it. And what we need to define now or derive now is the variance of these anomalous quantities. Therefore, in that case, by subtracting the normal gravity field from the true gravity field, we obtain residuals, and somehow residuals are of a stochastic nature. Therefore, we can apply statistical approaches for analyzing these anomalous quantities. Variance is defined, or variance for a stochastic variable is defined by this formula, and covariance of two stochastic variables y and x as x minus x, expectation of x of y minus expectation of y. Now, how this covariance equation is related to gravity field? If I replace a statistical operator with the mean value operator that I have already defined, and replace statistical expectation of x to normal gravity and both for y, and then I can write, for example, for gravity minus normal gravity for the first one, and the second one g minus gamma with the gravity anomaly. So in fact, covariance or the variance is the mean value of the residuals squared, or multiplication of residuals to themselves, or variance of gravity anomaly is the average of the squared gravity anomalies. Therefore, we obtained a mathematical model for the variance. But how is it defined over a sphere? So let me write it again. Average of gravity anomaly times gravity anomaly. Now I insert the spherical harmonic expansion of this gravity anomaly inside this formula. Summation over n, summation over m, delta g and m, y and m, spherical harmonics, theta prime or lambda prime. Prime means integration points. Summation over m prime over m prime, delta g m prime, y and m n prime m prime, theta prime lambda prime. So let me write this equation again and apply the operator m to it. The result will be summation over n, summation over m, delta g and m, summation over m prime, summation over m prime, delta g y n prime m prime, and the operator in here, 1 over 4 pi integral over the unit sphere, spherical harmonics with degrees n and m, and spherical harmonics of degrees n prime and prime. This is the orthogonality property of the spherical harmonics. And as you see, Kronecker delta means that when n and n prime are equal, then it will be 1. And when m and n prime is equal, then it will be 1 again. So this exists, this formula will be simplified to the following one. As you see, summation over n, summation over m, squared of gravity anomaly, degree n, and order m. It is actually the variance of the this is the variance of the gravity anomaly over the sphere. And as you see, if we take the summation over m for the square of gravity anomaly, we get a quantity which is a function of n in the degree. And this average variance is actually a summation of all degrees or variances at each degree. So the degree variance is an average signal per degree.